Hey everyone, and welcome back to another CTF Write-Up video. This is TJCTF. It was a 2-day CTF hosted by Thomas Jefferson High School, and pretty crazy, it's a high school competition because there's no way I could do these challenges back in high school. I'm going to be covering a number of challenges, 18 of them in total. If you want to skip ahead, there should be timestamps below. Otherwise, let's get started. The first web challenge is Web High, and we're just given a link. The screen looks a little bit confusing. If you open up the network tab, funny enough, you can actually see the flag in the background. But if we go over to network, refresh the page, we can see it's loading the secret SVG. And if we click on that, we get a preview of what that image looks like, and there's the flag. So it's just requesting it, showing it in the background, and then it's putting a canvas on top, or an HTML canvas, and drawing a bunch of stuff, but we can just look at the raw image. The next web challenge is swill-squill. It says ez-sql. We're given an instancer link and a download file. If we take a look at the download file, it's just a Python app. We're given an app.py, Docker file, flag.txt. Looking at app.py, we can see it's going to open a flag, and it's going to insert it into a database here. So it's inserting it into a note with the user admin. And the rest of this code is just creating an admin user and inserting some notes. So cool. So somewhere for the admin user, there exists a note with the flag. If we scroll and look through this app, eventually you'll find a SQL injection on the register route right here. So when we register, we're going to give it a name parameter. And it doesn't look like there's too much validation going on, so we can do some fun stuff with this name parameter. To actually exploit it, we're going to try to log in as the admin user. And to do that, we're going to pass a name such that it's going to be a close quote or 1 = 1, comment. And so when this executes, it's going to select star from users, so select all users where name is equal to empty string or 1 = 1. So this condition is always true. So it's just going to return all users, and from there it's just going to get the first user, which is thankfully the admin. If we go back up, we can see it's creating a new database, and it's just going to insert the admin first, so we'll be able to log in as the admin user and see the flag. To see what this looks like, we go over to the instancer. This is the thing, and here's the register with a name. So we type in that same payload, close quote, or 1 = 1, comment. We give it a grade of A, we hit register, and there's the flag. The next challenge would be web outdated, but I wasn't able to solve it. I have a feeling I'm probably missing something silly, but I'm excited to see the write-up. Next is web pay to win. It says this service is way too expensive. I can't afford that. I did hear that premium users get a flag though. We're given a shared URL and a download file. So for this challenge, basically we're going to be doing some hash cracking. There were two parts to it. The first part is, like I said, it's some hash cracking. Basically, we're going to get these two cookies, and we need to calculate this random value such that the two cookies, one is a hash and one is some data, match up. And so then we can start forging arbitrary cookie values. Once we're able to do that, there's this other part of the website where if we can forge those cookies and specify that our user type is premium, it'll open up this something from request args, this theme. And since we specify theme, we can specify a theme of flag.txt, and so it'll read the flag.txt and send it back to us. So for that first part, we need to be able to forge cookies so we can specify arbitrary attributes, specifically this user type. We want to say premium, not basic. To do that, you can kind of go through the code, but like I said, basically when you have a new user, it's going to call getRanBits24. And so the bug of this challenge is 24 bits is just not enough entropy for randomness or a token. You definitely need more. This is within the realms of offline brute forceability. It's brute forceable. This is just 3 bytes, which I think is like 16 million possibilities. So you're gonna, when you log in, you specify a username, and it's gonna generate that random value. And then using that random value and this data thing, it's gonna parse it into JSON, dump it, append the stuff, and send out the cookies. If we can calculate this value for a specific user, we can forge these arbitrary data things. None of this code is too complex, it's just not that exciting. So what we can do is we're going to take a data and a hash, and we're just going to start guessing what this random bits could be. And once we have a match, we know what the random bits are, and we're going to forge an arbitrary thing that says user type premium. And once we have user type premium, we're going to specify a theme of flag.txt, and it should just give us the flag. So that's what I ended up doing for the solution. First thing we need to do is copy some new values. So let's go to the website. Let's log in as SJP2. So we have a brand new user. It says upgrade to premium for a better experience. That only costs $999. Sounds good. So we're going to go over to edit this cookie. We're going to copy these cookies out. So this is the data cookie. You can see this is definitely base64 JSON. Make sure there's no equal at the end. It starts with that EY there. Then we need the hash cookie. Copy this. And we were user SJP2. So first thing we need to do is crack. So we're going to crack. So basically you just copy over the code from the app and just kind of massage some stuff around. So this is how they calculate that R value with the get random bits. We specify the username that we used, construct this object, and then we're just going to guess what that random value could be and calculate from there. And then we just try every possibility. We want to see if the hash we generate with a specific random value meets the hash that was on that server that we got in the cookie. And once we have a match, we know what random value is being used for that particular user. And every million requests I just print out to let you know how far it is. So that's step one. Let's do a crack. We'll do Python 3 solve. I'll probably speed up the video. And sweet, the cookie was cracked. So it took about 7 million guesses, and this is our unique identifier for the user SJP2. So we can copy that. We're going to take it over to this forge thing, and we're going to forge a new set of cookies. So we're going to say data username is equal to the same username SJP2, user type, now it's premium, which is what we wanted. We're going to base64 encode it. This is just the format of the cookies, and we print out both of the cookie values. So we'll comment out this crack thing. We'll go to forge, Python 3 solve. I guess I should make this bigger. Sorry about that. Yeah, I just did Python 3 solve. It prints out every million. This is the response we got. And now we have the two cookies. So this is cookie 1. We'll take that. We'll replace it here. Oops. Not like that. Then we'll take this cookie, the data hash. We'll put it here. And we'll refresh and see if we're a premium. And now we're on the premium site. So this is great. So now as part of that, you can specify a theme. And the theme we want is flag.text. I thought it was. I was being silly. I forgot that they moved the flag to the secret flag dir, and so we want to go here. So this is where the flag is. So we'll load that, secret flag dir, we'll view page source, and it should be in the styles, and there it is, not random enough. The next challenge is web easy SQL. It says just your average SQL challenge, nothing else to see here, trust. We're given a instancer link and a download file app.js. So let me start that, and we can take a look at the code. Thankfully the code is very small. I think there's only two things of interest. The first is it's going to create some jokes and put the jokes into some table, and then it's going to create this flag table, again using SQL, and the flag table is going to be some random table. So cool, and in that random table exists the flag. So the database is set up, and then there's only one real route, and it's this search thing. I have some consoles in here, you can ignore those. So it's going to grab the name parameter, and what makes this challenge fun is it says if name.length is greater than 6, bad request. Otherwise, it's going to continue. Normally this code is all in the query. I just separated it out so I could console.log it, but normally it's a select star from jokes where joke is like this. So we can see we have a SQL injection, but this says the SQL string that we get can only be 6 characters. So you can look online for a bit and see if you can do some SQL injections to read from, and specifically you need to do a union or a stacked query or something to read from a unknown other table. And what's even crazier is the table is going to be a UUID v4, so that's like, I mean, it's like 128 bits of entropy or 122 bits of entropy, so you know it's a long string, like 20 characters. So after a while you realize this is probably very impossible. So the trick to actually doing this, if we just run node, let's do a is equal to a, actually sorry, let's do name is equal to a, and then let's print out this. Console.log. We can see we get select star from jokes where joke is like a. The trick to this challenge is we're not going to specify a like that. We're going to specify a like this. And now we get select star from jokes where joke like a or b. If we look back at the code, it was name.length. Length applies to both strings and arrays. And so since this is an array, and the array just puts a little comma in here, which we don't care about, it makes, we can have as long of a SQL injection as we like, and from there we're just doing standard SQL injection stuff. There's nothing really too special. We're just gonna do some union queries, or we could do some union queries, or we could just use SQL map. I ended up just using SQL map. It's nice and simple. To make SQL map just run faster and not be as abusive on infrastructure, I didn't see anything in the rules that said you couldn't use SQL map, and since it's all instancer, I assume we're allowed to use SQL map. If not, yeah, sorry. But to do it, I think it's best just to run it locally first because it's super fast, and you can get kind of dial in on your SQL map query. So you can do node app.js, so it's running on port 3000. And then this is the URL I used at first to try to get things working. So SQL map localhost, this is the search thing. This is how you passed arrays in Node.js. That was also kind of important. Earlier they show that extended is equal to true as part of express. So I think this is what allows you to use that array syntax in a URL. So super important. So we say name 0 is equal to LOL and name 1 is equal to 2. Which is perfect. We're going to specify that our parameter is equal to name 0. We specify a high level and risk just because we're running it locally. You wouldn't want to do this on remote, but we're running it locally. It's super fast. We don't really care. We already know what the type of database it is SQLite, and then we're going to ask for the tables and we're going to dump them. So you just run this. We'll put it here, run it locally. Technically I already had it, but you can see the queries it's running, just doing these fun little union queries and stuff. And we can see it's a fake flag. Now we can run this remotely. Let's copy this. Now that we know what type of injection it's using, it's going to be much faster. Let me actually go back. So in our next query that we're going to do against remote, we're going to specify that we want to use technique union. And we can also get rid of this stuff. We don't need the levels and risk anymore. So SQL map, and we already know what type of database it is. SQL map doesn't have to do as much searching, which is nice. So let's replace this URL. Then we just take this. We're going to run it. So this will run on remote. It'll still take a couple of seconds. You just hit yes whenever you want. Blah, blah, blah. Do we want to test other parameters? We say no. And cool. SQL map was able to magically find the flag table for us. I often say I think SQL map is like one of the best tools ever made for security people. It just works. Now that we know what the table is, let's copy out this table name. We'll go back up to the previous thing. So we no longer need the tables. We know what table we want. It's this one, and we're going to ask it to dump that table. And SQL map just dutifully does it, and here is the flag. So easy peasy lemon squeezy. Fun. The next challenge is web back to the past. So we're given a shared URL and a download file. So for this, the download file, it's another Python app. We have an app.py. We can see in the app.py it's going to load the flag. And if we scroll down a bit, we can see we get the flag when our user year is less than 1970. It'll return the flag to us. So somehow there's some user profile, and when the year on that user profile is less than 1970, we get the flag. If you go through it a little bit more, you'll find out that they're using these JSON web tokens, and they encode these little packets. So every user object has an ID, a username, and a year. So to actually do this, we're going to be forging our own JWT tokens. I'm pretty sure the intended solution for this is not what I ended up doing. The fact that they put public key in the static thing, it makes me think that we're supposed to be doing one of those HSRS exploits, which I won't be talking about because we didn't have to. Instead, they used a custom JWT library, and there was a bug in the decode section of the library. If we go down to the JWT decode function, we can see that it takes in a token, a secret, and algorithms. The bug is the algorithms is only validating if the algorithms is available in possible algorithms, and it's just passed plainly. Let me go down to decode here. So it passes these two algorithms, and it's going to make sure that those two algorithms match this. But you actually specify the algorithm you're using in the JSON web token, which is right here. So it's doing some JSON web token, splitting, grabbing out the headers and payload and all that stuff. So the algorithm is specified in the token. And if we look at how it decodes it, it says if alg to use is HS256, or else if alg is to use is RS256, it'll do the decoding for those two algorithms. But if it doesn't match, it doesn't error out, it just returns the payload. So we can specify any algorithm as long as it's not one of those two, it just won't do any validation, which makes this challenge very easy. I'm pretty sure like I said, we're supposed to do, there's like this swapping thing that you can do with HS and RS, and you can swap them out, and the fact that they put the public key under static so that you could grab it makes me think that you're supposed to do that attack, but we're lazy, so if we see an easier way, we're going to do the easier way. So from there, we just need to forge a JSON web token that has a year that is before 1970, and specify an invalid algorithm so it doesn't actually validate it, and from there we should just get the flag. To do that, I copied out some code from just the encoding or decoding functions and put them in here. So they use this base64 URL encode, so I just copy that out. We're constructing a JWT, algorithm of none. We're specifying a payload, ID 1337, username, and here's the year, so year of 1337. Just from the code from constructing other JWTs, I just copied it out. You dump the header, you dump the payload, you join them together, you send a fake signature, I print it out, but then I just make the request. You just make the request to retros and include that as a cookie and print out the response, and we should just get the flag. So like I said, easy challenge, you just had to specify an invalid algorithm. There's another attack where you used to be able to specify alg none for JSON Web Tokens, but I think that's been fixed everywhere. Python 3, solve.py. We send it over, and there we go. We get the flag. TJCTF, very, very retro. Fun. The next challenge is web notes. It says obligatory notes website. We're given a instancer and a download file. If we open up that zip, this challenge is actually a race condition, which is pretty fun. It's going to load the flag here. So we have a flag file, and if we see where else the flag is being used, it's here. So on the GET request, it's going to do these two queries, and basically it'll return the flag if users 0 does not exist. So that means the users is being loaded here. So select star from users where ID is equal to this. So if we have a valid Node.js session, but there's no corresponding user object, we'll get the flag. I'm not sure where this would pop up in real life, but it's an interesting challenge. And like I said, it's a race condition because there is a delete users route here where it'll delete the user with that specific ID, and then it destroys the sessions. So what we need to do is we need it to start both requests, have them go through, and then delete the user, and then we need it to delete the user there, and then we make the GET request here such that users with this ID returns empty, nothing, and we'll get the flag. So you just try a couple of times and eventually you'll get it. And yeah, it was just a race condition. So this is what it looks like. I ended up using Python. Normally I'd use Go for race conditions, but I tried it in Python. It says to do that, you do with concurrent features thread pool executor. There's a bunch of different ways to do this, I think, but I just found some code online and I copied it. And to do that, yeah, so I created this function called checkFlag. It takes either a method of either a get or a post. And these are the two things we're doing. First, we get the request, and it'll do those checks to see if the user exists or not. And we also do the post to the delete to delete that user. And you just kind of spam them a bunch of times, and eventually you'll get lucky, and the condition will just match. And so on each of those, I check to see if TJCTF, the flag identifier, is in the text. And if it is, I print it out and I exit. Otherwise, the rest is pretty simple. We're going to register new users, username and password, allow redirects. We print out the cookies just to see what they look like. I log in again because I think it does some like allow session sort of stuff. It creates another session. I'm not sure if it actually helped, but I was just doing it. And then we do that race condition. I just send a whole bunch of GET requests, a POST request, and then a bunch of GET requests. And I hope that a bunch of them are lined up such that when we eventually call that POST request, we're already in the method for printing out the flag. And I just, you run it a couple times and eventually it works. And I wrap all of that in a while true. Yeah, that was pretty much it. So we'll do a Python 3 solve. We'll let it run for a bit. We're getting empty cookies, which is interesting. Cookie should not be empty. Oh, it would help if I was using the right URL. Let's go here, copy this out. The new URL. Cool, hopefully it works now. Now we get cookies, and there we go, we already have the flag. So somewhere in here it found the flag and it just printed out the response. And there it is, H1, TJCTF, duly noted. The final web challenge that I solved is web YOLO. It says, I found this website that makes me really emotional because it's so motivational. We're given 2 URLs and 2 download files. One is the challenge file and one is a admin bot. So if we go to this website, it says you only live once. Once what you can do a script, alert 1, script. We'll copy that over and see what we get. And nothing happens. But if we view the page source, we'll see 2 interesting things. First, we'll see that our injection actually works. Just based off of the syntax highlighting, we can see we actually do have script execution. But if we scroll down a little bit more, we see that this script has a nonce. And so this nonce is related to content security policy. So if we look at the headers that were sent as part of this request, we'll see that the server is sending a content security policy, and this policy specifically says, tells the browser only execute scripts if they include this nonce tag. Cool. So for this challenge, basically we need to be able to guess or brute force or bypass this nonce somehow. To do this, if we go to the server file that was included, you'll find this nonce generation code. Basically what it's going to do is if there's an existing nonce that already exists, use it. Otherwise, if not, for example, if you're a new user, you're going to use this as your starting nonce. And so what this code is going to do is it's going to start with this nonce, and then it's going to, for every request you make after that, it's going to generate a new nonce by taking the SHA-256 of the previous nonce. So if you know how many requests you've made since logging on, you can actually guess what the next nonce is. And so this was the bug. You're not supposed to have predictable nonces. Really, you should just be generating a random value every time. And so what you can do is you can calculate the number of requests that the admin bot makes, and then from there you know that when it clicks on your URL or views your URL, you know what nonce it's going to be using. And so when you do your initial injection, you just make sure the script tag has that nonce. And to do that, you just go here, you can see go to YOLO, it's going to make one web request here, then it's going to click submit, so that's the second request, and so the nonce will be on the third request. And so then you can just go, you pretend to be the admin bot, you make 3 requests, and you'll be able to grab out that particular nonce. That nonce ends up being, where did I put it here? This value. And we can actually show what that looks like. Let me close all the incognito tabs. Let's go here. Let me close this, or I'll just copy this. So to calculate it, so the admin's going to go here. They're going to type in admin, and then they're going to type in the flag. They're going to hit enter. And then let me, actually then they're going to go to another page, and we actually want to view source of this page. And so the nonce that they're going to use is 6CFA, which is the nonce we have here. So we just made 3 requests, and we can see we have the exact same nonce. So this ends up being our injection. So after that, it's pretty much standard XSS sort of stuff. Each user gets a note. And to access that note, you need the user ID. And to calculate the user ID, they store these cookies, which are JSON web tokens. And basically, you just need to parse out the JSON web token. You can grab the user ID, and then from there, you can make a request, and that request will contain the flag. To actually do this, this is the injection I used. So like I said, we're doing script with that nonce. We take the document.cookies, I split it on equal. I split because it's a JSON web token. I convert the base64, I parse it, I grab the user ID, just standard sort of JavaScript manipulation. Then I do a fetch request on that user ID. So this is the admin user ID, convert it to text. And then once I have it, I just send over that response to window location. I think it's a very long request, so I just split it on 2 other things and kind of grab the values. So it's somewhere between the main object and some random nonce, and somewhere in there is the flag. So we can take this, we'll make a new note. Let me open up webhook. Let's close this. Let's go to the root. And our name is anything, and this is our injection. We'll hit submit. Nothing should happen. We should get a CSP error, and we get one here because we don't have a valid nonce right now. But we can send this over to the admin bot, the URL we just created. Right now webhook says 12. We hit submit. It's loading. Hopefully this says 13 soon. Uh-oh. There we go. It took a second. Made me nervous. And this is our payload. So it says, you will TJCTF, you only live once. The first pwn challenge is pwn flip out. It says, my friend made this app with a flag in it. We're given a netcat port and a download file. If we open up the download file in Ghidra, the hard part of this challenge was just reversing. The actual exploit is super simple. In the file, there's a main function. And if we scroll down, we see that it's going to open up the flag file. So we can name this. I'm just typing L on the keyboard. So we'll say flag file. If there's no flag file, it can't open it. Otherwise, it's going to do an fgets on it. So we'll call this the flag buff. It's going to read that in, then it's going to close. It's going to ask for our input. The scanf that it's doing is here. It's doing a %15s. We can change the type of this. So we want data, and this is a terminated C string. So it's doing a scanf for 15 string into this. So this is our input. Then it's going to do an ASCII to integer on our input. So this is our input. We'll just call it val. What's interesting then is it's going to do input plus input val and do an offset and print the string there. So a little bit confusing, but basically what this is going to do is it's going to, it's kind of like doing an array offset, but we get to pick the array offset, and it's going to print the string at that array offset. And it starts at input, and then we get to pick how many characters past we want to print the string at. And if you count 8, we'll say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. At 16, there's flag buff. This is being accessed by bytes, so we need 16 times 8, which is 128. So if we put in the number 128, it's going to print out the string, 128 characters down the array, which is our flag. So we should just get the flag. I wrote a Pwn tool for this. I just copy over this template, but we really don't need it. Instead, we can just netcat to it. So we'll copy this. We'll netcat. It's asking us for our input. We're just going to type in the number 128, and we get the flag. The next challenge is Pwn shelly. Now we're given a netcat port and a download file. So if we open this up in Ghidra, we can see it's a nice simple main function. There's a buffer. It's going to give us the address of buffer, which is really nice. It's going to do an fgets. This is going to give us a buffer overflow by an extra 256 bytes. It's then going to loop over character by character and make sure that the character does not contain the byte OF or O5. And if it doesn't, it'll say OK and return once it hits the end. If you check the protections, you can see that we're allowed to use shellcode. Non-executable stack is disabled. So we can execute shellcode. What's tricky is you need the OXOF and OXO5 bytes in your shellcode for calling syscall. I imagine there's probably another way to call syscall or do interrupts or something clever. I didn't know what it is, and I really don't like messing around with shellcode. So for this challenge, I ended up just wrapping around to get the flag. But I think the idea was you were supposed to write a bunch of shellcode and somehow bypass this. But like I said, I did ROP code. If you're not familiar with ROP code, this challenge might be a lot. I'd highly recommend. I have other beginner videos on my channel that kind of talk about ROP code, but I'm just going to go in to this challenge assuming you know what ROP code is. Cool. So this is standard Pwn tools. We just import stuff. We disable warnings. We load everything up. Here we're going to grab that address leak that is given to us. From there, we calculate where the buffer overflow occurs. I see it's at QAEC. I just do a Pwn cyclic, see where it crashes, all the very standard stuff. To construct the ROP code, we were missing a gadget. And so since we're allowed to embed shellcode, I just inserted that gadget that I needed. And specifically the gadget we needed was a pop RDI ret. So I construct that shellcode and I put that in, and so that later we can just refer to that gadget. We don't know the libc that's running on the remote system, and so we need to print out different addresses in the global offset table to figure out what remote z is. So I construct some ROP payload to just print them out. So first, I do a pop RDI thanks to that shellcode gadget we just inserted, and then I pop out the global offset table entries for puts, setbuff, and printf, and then I just call puts on those. And so that'll print out all three of those addresses. We can print those out, and then we can use one of the libc databases online to see which one it is. I had a feeling they were using Ubuntu 22, and I was also using Ubuntu 22, so I just ran it locally and remote, and I saw I was using the same one, so it's just Ubuntu 22. And then once we're done printing stuff, we just jump right back to the start of main. And so now we have our info leaks into libc. From there, and this is how we send it. From there, this is how we receive all the addresses. So we're receiving the puts address, receiving the setbuff, receiving the printf. From there, we calculate the base of libc. So we just do puts minus the symbol for puts. So now libc address is correct. And then from there, now that we know where libc is, we can just call system bin shell. We use Pwn ROP tools again for that. So we have to insert a ret in there because of some stack alignment issues. If your stack entry ends in an 8 instead of a 0, there's some calls in libc that aren't happy. So you just insert an extra ret in there, and that way the stack is aligned correctly. But then we call ROP system. We search for the string bin shell, and we should just get shell. So really not too bad of a challenge. We'll do Python 3, solve.py. Actually, let's jump into an Ubuntu box. Python 3, solve.py. Does a bunch of stuff. It's loading gadgets, and we say ls, and we can see we have shell. So now we need to grab the remote port. I should already have it loaded. Yep, let's jump into remote, and let's do it again. So we're connecting to remote. Oh, this way faster. We do ls, and there we go. There's the flag, so we'll cat it out. And it says Sally sells, she shells. So fun challenge. The next challenge is Pwn groppling-hook. It says grapple to safety. We're given a netcat port, a binary Dockerfile, and main.c. So source code, which is nice. It says grappling hook or groppling hook, so it implies that we're going to be ropping. That's what the challenge was. So we're given a main.c, which is nice. So there's this laugh function, which is an exit function. There's a win function, which opens and prints the flag. So we have our win condition. And then there's this pwnable function. And so this is where stuff actually happens. And then there's just a main function, and all it does is buffers and then calls pwnable. So in the pwnable function, it defines a buffer of 10 bytes, and then it reads into that buffer for 56 bytes. So we definitely have a buffer overflow. NX is enabled, so we're not going to be doing any shellcode. It's just a standard ROP challenge. Thankfully, pi is not enabled, so all the addresses are known. So this win function is at a known address, which is nice. So after it does that buffer overflow, so now our stack is clobbered with whatever stuff we put there, it's going to do some interesting code where it actually checks what the return address is going to be when this return is called. So if you remember, everything's stored on the stack. We have our stack frames. It's going to check the next stack frame and ensure, so it's going to move the stack pointer up, pop that value into RAX, and compare it and make sure that it's in a known value for where main should be. So between the values of 1262 and 128A, I guess is where this code should be returning. And if it is not in those values, it's going to call laugh, which is that ROP detected and denied exit, which is not what we want. Otherwise, it'll push that return address back onto the stack and it'll return and jump to main. So somehow we have to bypass this such that we can call win instead. The trick to this is if we look in GDB, we're going to do GDB out. Let's break on, I have it stored somewhere, pwnable plus 70. Let's run. We'll send in some garbage. Cool. So I think the key insight to this one is normally when we do wrapping, we overwrite just that first entry, but there's usually many function frames on the stack. And so we don't have to overwrite the first one. We could just overwrite the next one. And that was the trick to the challenge. So like if we print out stack, let's say stack 20, this is where things would be returned. So this is the stack, this is our input buffer, some other stuff. This is the RBP, the frame pointer, and here's the return address. But if we look right here, there's another return address here. So after main is finished, it's going to jump back into libc at this address. But since the code checks to make sure we don't clobber this one, we'll just clobber this one. So in here, we're going to put the win address. So the code now, when it executes in this pwnable function, it's going to click return, and then it's going to go here. And when this return is executes, instead of going into libc like it's supposed to, we'll have it go into the win function. So nice and simple challenge. We're going to do a pwn cyclic 18. This is just going to fill up the buffer. And then after that, we're going to overwrite with the correct return address to main because we're not allowed to clobber that one. Then we're going to put in some garbage because there was just a garbage stack entry. And then we're going to put the address of win. But we actually do win plus 1. But yeah, that's it. The reason we do win plus 1 is just stack alignment issues. For some reason, this is calling libc, and because the stack is just off by 8 bytes, you just have to insert an extra one in there, because if we look at the instructions, so examine, let's say 10 instructions at win, if we go to this byte instead of this byte, we ignore this push call, and so that just that way our stack ends in a 0. We just got lucky that the first thing ended up being a push, and so we can ignore that push so it doesn't modify our stack pointer. But you know, there's other tricks. We could have put an extra return in there or something like that. Yeah, and that was the challenge. So we can try running it. Python 3, solve that pi. Oh, and it's already running on remote. So this is what we sent it. We sent it all those A's. Then that's one stack address. We ignore the rest. That dead beef has extra space, and then the win condition. And we get that back the flag. It says, this is my quest. The next challenge is pwn formatter. It says, give me a string, any string. We're given a netcat port and a binary. So based off the title, we can guess we're doing a printf exploit. If we open it up in Ghidra, it's definitely an interesting challenge. Basically, it asks us to give us a string, and then it's going to do a printf on that string, and we get 256 bytes, so we get an arbitrary long printf. Then it's going to call this r1 function, which is going to change this parameter here, and then print among us. And then when it calls the win function, it's going to check and see if this xd variable is equal to this. So these things aren't hard, but it's just it's an interesting challenge. There's also this R2 and R3 that aren't actually used anywhere as far as I know. So definitely an interesting challenge. But as long as we can do that, it'll print out the flag for us. Like it loads the flag and it says you win, and then character by character it prints out the flag. I think it's down here somewhere. So cool. So we need to get it to print the flag. Like I said, we need this condition to be true. So this global variable xd has to be equal to this. Cool. And And there was one other thing. At some point it calls that R1 function I already showed, and it's modifying this xd function, and it's adding 2 to the value. Cool. So since we have printf, we can, when we have a printf, and it's also a position independent executable binary, or it's not a position independent executable binary, we know where this address is stored, which makes this nice and simple. So because of that, we can use printf to write a value to this. What we really need is a value. The value we write to this isn't actually that value we saw earlier. We actually need to write a pointer to that value. So to do that, we're going to be doing 2 different printfs. First, we're going to do a printf to some random section in a read-write place that has just a known address that we just pick a random one. We're actually going to write the value we need, -2, and then we're going to write to xd and put the address of that address we just wrote to. And once we do that, the 2 conditions will be met. And so when we come here, it's going to offset that address of xd, read this value, that'll match, and it'll print out the flag. To do it, thankfully it's very simple. Pwn tools is absolute magic. We're going to be using this format string payload thing, and we specify 2 different writes. So like I said, first we're just going to pick some random address. You can load up GDB and just find a random address in the read-write section. That looks good. So I chose 4035000. Then I submit that value, -2, because eventually it's going to do that add to. And then wherever that xd symbol is, we just need to write the value of that address, so you can see they match. And yeah, that's pretty much it. You have to calculate the offset of where your printf actually starts. So here it's 6. To calculate that, you just do this, p.interactive. This is how I do it. There's probably other ways. I just send 8 A's, and then I do a bunch of %ps. And so if we run this, make Ubuntu 22, Python 3 solve. We'll see this is our response. And so we get AAA, this is some address, null, or sorry, these aren't addresses, something, and then here's 0x414141. So if you count, this is 1, 2, 3, 4, 5, 6. It is the 6th %p until we get our reflected content. So we know it's offset 6. And you pass that into format string payload. And so format string payload now knows where your addresses actually start. But like I said, you just give the rights to the program, and from there it just works. So let's do Python 3 solve.py, and somewhere in here we should have the flag. Here it is, TJCTF just formatted. So nice little printf challenge. The last pwn challenge is pwn teenage game. It says what happens when the baby game grows up. So there was a game in Pico CTF this year that was very similar, so it's kind of an extension off of that. We're given a netcat port and then 3 download files. Cool. So let's take a look in Ghidra first. There is a win function, which is nice. So if we can jump to this win function, it'll call bin shell. In the main function, thankfully everything is labeled pretty nice. We can see init player, so this is our player, init map, so this is a map. It's going to loop over while the player is not equal to these addresses. So the very end address, we get to move the character around. And yeah, that's pretty much it. There's this move player character, so it's going to see if it's a WASD, so WSAD for moving around. And there's also an L command for changing the tile character. I think by default it starts out with a @ sound. Yeah, @. And so you can just kind of move around and do stuff. The trick to these challenges is they're always, I guess, kind of buffer overflows. We get to kind of manipulate different things on the stack. So there's obviously, this is a very large buffer, but we can go off the map. So if we go over here, we just wrote some value on the stack below with the value of @ which is pretty fun. So we can kind of manipulate just different different bytes on the stack. So to solve this, what I ended up doing was abusing the stack of frame above this function. So normally you like overwrite down, which is also up the stack. It's kind of confusing, but you know, if you're doing your buffer overflow, it's going to flow down to the return address for that stack frame, and you abuse that one. The problem is when you move this character, it overwrites the previous place with a period. And the function doesn't call return until you go down to the X in the bottom right corner. So you can do a bunch of manipulation down here, but if you overwrite the return address, it's going to be periods instead of whatever value you wanted. Like if you wanted 4, for example, it won't be a 4 because it's being overwritten by a period until you get to the X where it calls return. But if you instead write values above the buffer, you can go into the stack frame of whatever function is being called and setting stuff. And it happens that you can actually overwrite the return address for this above function. I think the above function ends up being this function, this move player. So we're actually going to overwrite the map object here with the player tile, and then it calls return. So what we're going to try to do is get this to be equal to the return address on the stack for this move player function, and we're going to overwrite it with just a single byte, so that instead it points to the win function. And yeah, that's pretty much it. To actually see what this looks like, let's jump into GDB. We'll run it real quick. We'll hit cancel. So let's do a stack 20 maybe. So here we can see this is our map. And right now we're in read and a bunch of other stuff. So if we were to just go up, we can see here's a return address. And so right now it's going to return to 8C. But we can figure out the address of the win instruction. So let's examine hex at win. We can see this is actually the one we want. I think we can just do print win. It's probably better. We can see right now the win address is DF. So if we can overwrite this last byte with DF, chances are we'll win because we can see it's 838C, 83DF. There's just one complication. When we do the overwrite, similar as a previous challenge, we get a stack alignment issue. So to do that, we can examine, let's say, 5 instructions at win. We'll see that they do the same push RBP thing. So if we just ignore this push RBP and instead jump to E4, things work out fine. And we also, thankfully, we got very lucky too. We're jumping back. Thankfully, we only get to do a single byte overwrite. But thankfully, the win function and the return address are very close to each other in instructions. So we're jumping back from move player back to main, I think. Move player, yeah. And if we look main, let me scroll over, is this, and win is very close. And since we only have a single byte overwrite, it's calling back to 13A2. This win function also starts with 13. And so because of that, we only have to do a single byte overwrite. So everything ends up working out. The actual exploit for this, I guess the last part is you need to calculate how far to the right you go to align up with that byte. So I know that the map is like 89 characters wide. I just go 89. I assume it's back a couple, so I do 16. Then I poke up and poke down on the map and see where E4 is being set on the stack. And then you see that you're wrong. You just move it around a couple times. I saw I was off by 7, so I move it 7 to the left. And yeah, otherwise that was it. So we're setting the character to E4. We're going up by 4. Then we go to the right a whole bunch, whatever this is. And at that point, all we have to do is press up. And as soon as we do that, it's going to overwrite the return address, and it should just jump to the win function and spawn a shell. So we can run it. Let's do Python 3, solve.py. Cool. So we have E4 right here now. All we have to do is press W and enter. And at this point, we are in a shell. We can see it didn't print out the map. The return address was called, but it went to the win function. And now we can do ls, and that was it. So we can do cat flag.text. And we get so many new features, but who will stop the underflow? So, fun challenge. Next up is rev wtmoo. It says my cow keeps eating all the flags, and we're given a challenge binary. This is the binary, thankfully relatively small. We insert some text. From here, it's going to loop over and do a bunch of substitutions depending on what type of character it is. And it just does all these substitutions, and at the very end, it compares to see if your substitutions equal this string. And if they do, it tells you that you got the flag correct. And yeah, and for these substitutions, like I said, it's going to check to see if the character is between this range, and if it is, it does this substitution. It's going to subtract 3C or OX3C from whatever that flag value was. There's probably clever ways to do this. I tried running anger on this. Anger wasn't working for some reason. It just wasn't closing, so I gave up pretty quickly. So instead, I ended up just doing like a very sloppy, dumb solution that was very fast and ended up working. So here's the guess. And these are all the different offsets that the program is doing. So you can see sometimes it subtracts 15, it does a plus, it does a plus space, it does a minus 3C. So I took those offsets and I just run all of them. I perform all of those offsets on the original guess, and then I just kind of guess what the flag is going to be. So like I said, for each of the characters in guess, I just calculate that offset and make sure it's actually a printable character. And if it's not, I just put in a period. So like all the alignment works. And when you run it, you can already see it there, but Python 3 solve, 2.py, oops. this is what we get. So what I did is I copied this over. I just placed it down here. So we can kind of see what things look like. We can see TJCTF. So this is the lowercase characters. So lowercase characters here are probably good, not necessarily, but and sorry, scrolling back, you can see there's like lowercase, uppercase, low numbers, and high numbers. So that's kind of the different categories I'm going with. We don't really know what this one is, but it's probably not uppercase. If you see a 7 and 8 here, that's the only place there's high numbers, so this is probably high numbers. Here, if you look through, uppercase seems a little bit strange because this is definitely a bracket here, and it has a P here. So I'm going to guess that I see some zeros here and a 1, so I'm just going to guess this is low numbers. And here, this must be uppercase because everything else was taken. Cool. From there, we just have to align everything. Oh, it doesn't include brackets, but we know where those are, so we'll put brackets at the start and end. And I'm just overwriting the lowercase one. From there, we just kind of go up and down whenever we need a character, and we see which one matches. So we need a character right here. We go down. There's no high number. There's no lowercase number. This is an uppercase number, but there is a uppercase letter here. So this is probably a capital M. Here, we need something. This is not a high number. This is a low number, so it could be an O. So that actually looks good. Scrolling down, we need another one. This is not a high number. That's not a low number, but we have an uppercase O. That works. And you pretty much just go through and do this. We'll copy a 0 out. Here we need something. We got another 0. Oops. We can see the next one is also a 0. There's just a bunch of zeros there. Then we have some hash, so we need a 7, where we can see the 7 here for high numbers. We have an 8 for another high number. And then we have a 1 here. And that ended up being it. This was the flag, so not too bad of a challenge. There's probably smarter ways to do it, but this worked. The first forensics challenge was beep boop robot. We get beep boop, it sounds like a robot, sus, and we get the flag format. So if we download this, there's a bunch of, if you listen to it, it just sounds like Morse code. So it's just a Morse code challenge. You can go to Morse code decoder, you already saw it, audio online. You go to the first one. Somewhere there's an upload file. Let's upload a file from downloads. Robot.wave, and let's play it. So you won't be able to hear it, I think, but you can see it's just decoding the flag. It says, "Hi, how are you doing?" Sweet. And so we can see it printed out the flag. It says the flag is TJCTF. This is all one word lamo. And everything needs to be one word, lowercase. You do that and you get the flag. Next is forensics, nothing to see. It says nothing to see here, just move along, and we're given this image. If we take a look at the image, it just says nothing to see here. So we can run binwalk on it. So we'll do binwalk, nothing, see if there's any hidden files. And there is. There's a zip archive, it's encrypted, and it has a file named flag.txt. So perfect. So we'll do binwalk, we'll do extract, M is kind of like a recursive binwalk, and we'll do nothing. Sweet. We can go into that folder. We can see there is a zip file and a flag file. If we cat out the flag file, it's empty. That's because the zip file is encrypted and we need a password, zip 39, something like that. We don't know what the password is, but it must be somewhere in here. So we can run strings on nothing. And if we do, these don't quite look like strings, but if we scroll up a little bit, we're looking for something that could be a password. We keep scrolling up, and eventually we found this, panda something something. This looks like a flag format. They've been doing that underscore sort of hash thing as a flag format, so this is most likely the password. So we'll copy that. We'll go back into that nothing folder, and we'll unzip 39 something. We'll give it the password, replace, yes, cat flag.txt, and there it is. The end is not the end. The first crypto challenge is crypto baby-rsa. It says small numbers for small messages, and we're given an output.txt. If we open up the output.txt, we can see these numbers. We're given an N, E, and C, so definitely an RSA challenge. We can see the N is pretty big, the E is just 3, and the C is like half the length of N, maybe even a third of the length of N. So it's very strange that C is that small. Normally, like when you do the RSA encryption, you're doing everything modulus N, and so the numbers are, roughly size N. But the fact that C is so small means that it probably hasn't wrapped around, which means that the message is probably very small. And if the message is pretty small, we can probably just do a cubed root. So normally it's like, m to the power of 3 mod N. But since, like I said, it was never wrapped around, we can pretty much just ignore this mod N And so we're saying c is equal to this. If we just take the cubed root, I don't know how to do that, but root 3, I guess, of c, we'll get out m. So nice simple math, and that's what the solution was. So I load in the values. I use GMPY just because it does the numerical calculations very well. We're doing an integer root of c and e, so just ciphertext and 3. And then I print it out again. I do a long to bytes because it's going to come out as a number. And we should just get the flag. Python 3, solve.py. And there we go. It says 3s are so much fun. The next challenge is crypto ezdlp. It says 1 ezdlp, and we're just given numbers.txt. So if we open that up, we can see we have a g, s, and p. It's calculating g to the x, s equals mod p, and the flag is just x. So this is discrete log problem. One thing we can look at and see if p is smooth, so if p has many factors. So we can go to factor.db. I feel like I'm a nerd now. It used to be if I typed FAC, it went into Facebook, but now it goes into factor.db. But we can see that this particular prime has, or it's not prime, it's a composite number. It has a lot of prime number factors. And so we say that is smooth. And so there's an algorithm called, I don't know if I'm saying it right, Polig-Hellman, that we can perform. We could look up Polig-Hellman, or we could just have Sage do it for us. So Sage is just a math tool. It's kind of like a Python-like interface, but it has a bunch of like number theory and crypto functions built in. And they specifically solve discrete log problems for you. So we're just going to do the discrete log problem. Under the hood, I think it does Polig-Hellman. I think it does a bunch of different algorithms, but I think one of them is Polig-Hellman, and it just does it for you. So we're going to say that we want the discrete log. Actually, let me recap. What we're trying to calculate is x. And so normally this is a very hard problem. G to the x is equal to s mod p. Using the discrete log problem, we're able to calculate this x. And this is like a computationally hard challenge. Like usually if you do everything correctly, it should be like, as hard as brute forcing. But thankfully, since normally to do that, you need p to be prime, and there's probably some group properties you need to refer to a real crypto expert. But since p is smooth, we can do this algorithm and just kind of crack it a little bit faster. Like I said, we're gonna have Sage do all the heavy work. So we're doing this mod. Both numbers need to be mod p. Sage has like this like typing system, and it knows what fields and stuff integers belong to. And so you just kind of specify that this s belongs to mod p. Now that we loaded Sage, you just type in Sage if you have it installed. We're gonna paste in this code. We're gonna wait a couple of seconds. And there we go. The final crypto challenge that I solved is crypto iheartrsa. It says, I sure do love RSA. The question is, do you? We're given a netcat port and a download file. If we look at the download file, so what this is going to do is it's going to take the hash of our flag and then convert it to binary, and then add a 1 to that binary and make it 256 bytes long. So basically this hash means that it is a full like 256-bit number. Cool. So basically it's just adding whatever 2 to the 256 or 2 to the 255 is to the hash of the flag. Anyways, we just have some large random number, basically. That's 256 bytes or bits. Then it's going to generate a P, a Q, an N, and an E. And so the real bug of this challenge is right here. So normally E is like 3 or something, and you kind of want the numbers to be big so that you get, like when you do that RSA, you want that, there's that modular component, everything's mod n, and you want it to like, wrap around many, many times. And that's where you like, that's really what makes it unbreakable. But what they do here is they're going to figure out which E is the first E such that it wraps around for the first time, which is a little bit strange, but it also means that we can brute force it. That was pretty much the solution. So when we connect to the service, they're going to calculate what M, so what ciphertext is such that it just barely for the first time wrapped around N. And we can just brute force that. And it's going to give us M and N. And so our job, if we knew, I think we need to figure out the hash, but if we knew what E is, we'd be able to calculate the hash. And to do that, we're just basically going to brute force and take a bunch of roots. So it's very similar to the first crypto challenge, just with a little bit more brute forcing. And yeah, that's pretty much it. It wants us to return the hash as the answer, and so we just need to calculate that hash. So this is the solve script. We're going to connect to the remote port. We're going to grab out the M and M. So we have those two values. And like I said, we're pretty much just going to brute force it. So we don't know how far around it wrapped. when it did that pow, but we can just guess, like maybe it wrapped around once, maybe twice, 3, 4. We can just guess. I did it up to 100, and it finds it pretty fast. And we also we don't know what integer root it did it to. So this is the value of e. So really I should call this e, but we don't know if it was raised to the power 3, 4, 5, or 6. But we can brute force both of those at the same time, and if we find a solution, one of the solutions should probably be correct. When I ran it, it worked the first time, but maybe I just got lucky. So we can try Python 3 self.py. Sweet. Let me copy this and paste it real quick because there's a timeout, and it worked. Cool. So we got the m, we got the n, and these are the different solutions. So when I print it out, we can see there's a 2, 4, 8. So these must be the e's, and this is how many times it wrapped around n. So to do the wraparound, so it's 23. So I'm doing m, which was the message that we were given, n, which is what we were given, and I'm multiplying n by 23 and I'm adding it. So when you do the modular arithmetic, obviously you'll get out m, but we're just bumping it up. So when we do that integer root, everything works out correctly. So here it's saying if we wrap it around 23 times, and we take the 8th root of it, this is the hash we get. The hash was around this last time, so I just returned this one, the same length, so I just recognize it. Yeah, so we just return this hash and we get out the flag and it says, I love RSA as much as I love my mom. So very cute. All in all, the CTF was a lot of fun. Thanks to the high school for putting this on. Very impressive stuff. I like that it was a very educational CTF, like a lot of the fundamentals and all the pwn challenges. They covered everything. I don't think there was a heap challenge, but they covered all the other exploitation techniques, which is just a great learning experience, and I had no infrastructure issues. So yeah, thanks for the CTF, and I'll see you at the next one. Cheers.